City College, and my mentor for this project was Professor Gautam Chindu, who is a professor of mathematics at City College, and the research project we worked on is entitled Questions in the Distribution of Prime Numbers. So first we have to define, well, what is a prime number? So a rational prime number is any number greater than 0 whose only proper divisors are itself and 1. So proper here meaning our quotient also belongs to the set of rational numbers. And all integers can be uniquely expressed as the product of some prime numbers, assuming they're not prime themselves. For example, taking the number 100, we can say that that's 2 squared times 5 squared. So this is also known as the prime factorization. So knowing this, several questions would naturally arise. So how do you decide if a number is prime? And if it's not prime, how do you factor it into its prime components? So answering our first question, we asked, is there some prime p that divides our so-called prime that we're testing? Here we give the variable n. So for example, taking the number 299, we ask, is there some p that divides 299? And this vertical bar here is a shorthand asking, well, does that divide our number? So we test using our known prime. So we test this 2 divided, this 3 divided, this 5 divided. And then we get to a point where we have to ask, well, what number do we stop? Where do we stop testing? Do we just go on forever? What happens? So what we do is we do a little test. We take 299 and we say, well, if it's not prime, we can write it as the product of 2 prime numbers. Here we say p times d, where p is the smaller of those 2 factors. So using this inequality, p is less than or equal to d, what we do is we take that and we multiply both sides of the inequality by p. And doing something on both sides of the inequality preserves the inequality. So on one side we have p times d, and on the other side we have p times p, or p squared. And if you recall, we said that 299 is p times d, so we go ahead and replace that there. So our new inequality is 299 is greater than or equal to p squared. Solving for p, we have p is less than or equal to 299. So what that means is, at best, our smallest factor p is less than or equal to the square root of our number. Here, the square root of 299 is 17. So we only need to test up to the square root of our number. So we continue the 7 divided, 11 divided, up until we get to 13. And 13 does divide 299. In fact, 13 times 23 is 299. So as you can see, this gets really tedious if you want to generate a large list of primes. So you don't actually have to go and test every single number in that list. We can use another method, which is called the sieve of veritasities. This is just a fancy name for a technique to quickly generate a list of primes. So what we do to use this sieve of veritasities is first we cross out the number 1, because 1 is not a prime number. So then we go on to the next available number 2, and we cross off its multiple. So we cross off 4, 6, 8, all the way up to 20. Then we go on to the next available number here, 3. We cross off its multiples. So 6 is already crossed off, 9, and then 12 is already crossed off, and we go up to, in this case, 20. And then the same rule applies here. We only need to test up the square root of our largest number. So the square root of 20 falls somewhere between 4 and 5. So the next available number, which would have been 4, is already crossed out. So once we get to that number, we've crossed out all possible numbers. And the remaining numbers would be our primes. So here, all the primes less than 20 are 2, 3, 5, 7, 11, 13, 17, and 19. So this is just a quick way of generating a list of all the primes less than some number. So one of the major points of our research was verifying the work of 2 other mathematicians by the name of Andrew Granville and Greg Martin in their paper entitled The Prime Number Races. So what they did was they used something called modular arithmetic to divide these prime numbers into categories. So they're trying to find the distribution of prime numbers. So modular arithmetic is very similar to standard division, except in division you're more concerned with the actual quotient, and in modular arithmetic you're concerned with the remainder. So for example, take the number 6. When you divide it by 2, our answer is 3, remainder 0. But with modular arithmetic, we say that since we get a remainder of 0 when we take 6 and divide it by 2, we say that 6 is congruent to 0 mod 2 because it has a remainder of 0 when divided by 2. So taking the number 3, 3 divided by 0 is 0, remainder 3, so it falls into the category of 3 mod 4. 5 has a remainder of 1 when divided by 4, so it falls into this category. And it turns out that the primes are more or less evenly divided into these 2 categories, 1 mod 4 and 3 mod 4. But there is an affinity towards 3 mod 4 over 1 mod 4. And 3 mod 4 is in the lead just about 99% of the time. And A similar winning of some mod categories over others holds true for other mod divisors. We tested mod 3, mod 5, and mod 6. And an interesting thing is that the losers of any prime number race are congruent to some square number mod. And so what that means is, for the case of mod 4, we have 9, which is 3 squared. Mod 4 is congruent to 1, which is why 1 mod 4 was a loser in the prime race mod 4. So the focus of our research is taking the theory of prime number races and applying it to completely different sets of numbers. The number set that we were working with are called Gaussian integers. And now Gaussian integers are numbers of the form a plus bi, where a and b are both integers, and some of you may know this as complex integers. So the same theory of primes holds true for this as well. The same theory of prime numbers holds true for Gaussian integers as well. So Gaussian integer is a Gaussian prime only if its only proper divisors are plus or minus 1, plus or minus I, and multiples of itself by plus or minus 1 or plus or minus I. So for example, the number 1 plus 2i, which is a Gaussian integer, the only other ways of representing that number, we can represent it as negative 1 times negative 1 minus 2i, or I times 2 minus I. But since these numbers have this identical what are called norm and different theta, we say that 1 plus 2i is a Gaussian prime. So we'll get to the theory of norm and theta in a second. So sometimes a rational prime is also a complex prime. So only numbers that are form x squared plus y squared, where x and y are rational numbers, can be factored into Gaussian prime. So what that means is if you can take a rational prime and express it as the sum of two squares, we can actually factor that into, we can expand it into complex conjugate form a plus bi times a minus bi. So taking the number 5, we can write it as 4 plus 1, which is 2 squared plus 1 squared. And because we can write it in that form, the sum of two squares, we can expand it into a Gaussian prime, 2 plus I times 2 minus r, or we could have just as easily said 1 plus 2i times 1 minus 2i. So because we can expand the number 5 is not Gaussian prime, but 7, which is a rational prime, cannot be factored or cannot be expressed as the sum of two squares. So we say that 7 is both a Gaussian prime and a rational prime. So now the angle of Gaussian prime is calculated taking the arctan of B array. So what happens is the idea of mod categories doesn't really translate so well from rational primes over to Gaussian primes. So we needed another way of separating these primes into categories. So what we did is we divided all the Gaussian primes into categories based on the angle that they make with the real axis. So what that means is taking Gaussian primes are really interesting because we can actually have a graphical representation of them. So for example, taking the number 1 plus 2i. So this number has two coefficients. It has an a, which is 1, and then a b, which is the coefficient in front of the imaginary number, which is 2. So what happens is, when we're graphing something in traditional Cartesian coordinates, we have an x and y coordinate. Now, with Gaussian primes, instead of having an x and y axis, we have a real axis and an imaginary axis. So when we're graphing this number, we look at the real coefficient here, which is 1, and we go over that many units on the real axis. So here it is 1. And then we look at the imaginary coefficient, which is 2, and we'll go up 2 units on the imaginary axis. So here, 2. So you see how every Gaussian integer has some coordinate in space here. That would be 1 plus 2i. So with that, we have two things associated with it. We have what's called a norm, which is the distance